Testing, testing, 1, 2, 3, testing, testing. Testing, testing, testing. Got to check the audio. Oh. Yep, okay, that's good. Hi guys, sorry for the delay there. Yeah, sorry about that. Just one of those mornings, you know? There we go. So, a couple of announcements before we get started. All you fancy meat computers, I didn't forget. Ha! So, number one, I've been asked by Mark to talk to you guys on the subject of Git repos. So, I just checked in with Mark this morning, and it seems that as of, 10 minutes ago, whereas the due date was 3 minutes ago, there are 11 people in the class who have not submitted to us their Git repo information, which means at this point that they're not going to get any marks for Lab 1 and 2. There are some people who, there's like one person who has the wrong permissions enabled for the Git repo, which, we can't mark your work if you don't give us access permissions, so if you wouldn't mind doing that immediately, that would be fantastic. And there is also a couple of people have submitted empty repos, which, of course, again, if there's nothing, even if we have access to the repo, if there's nothing in it to mark, then you won't be getting any marks for anything. I think this is kind of like probably in line with the standard number of people who just don't submit things. Apparently 4% of your final grade for this course, or 8% if you take the two labs together, isn't enough to whet people's appetites, so, that is what it is, I suppose. One thing, though, just so you guys know, the idea is that you have one repo into which you put everything you're submitting for this course, because it actually takes a fair amount of time for Mark to, process all of the information you're sending. So it would be in everyone's best interest if that if the repo that you sent him, the CS1XC3 repo, all of your submitted work will go inside of that repo. That way we don't have to keep, reopening and re-adding all kinds of extra information that you guys send us. So, yes, the whole point of using GitHub is to make things easier after the initial startup cost of setting things up. So, yeah. So, one or two people sent us new information for their assignment 1 repo, as instead of putting an assignment 1 directory inside of their the CS1XC3 repo that has all of the labs in it. So if you could just put everything in one repo, that'd be fantastic. Hopefully everybody gets this. So, item number two. So it turned out that there was a slight technical problem with the manner in which I wanted to give you guys the code templates for assignment 1. And it turns out that that also has an effect on how Lab 3 was going to be delivered. Specifically, I have set up on my GitHub a couple of repositories which serve as the starting point for both Assignment 1 and Lab 3. So the idea is that you guys fork those repositories, and once they have been forked, you can modify them without, attempting to send changes to the public repository into which which I've set up very specifically for the purposes of these assignments. Separation of concerns. It turns out, though, that you can't make a private fork of a public repository on GitHub. It's just disallowed. So there's an alternative procedure that you're going to have to go through in order to perform what's called a mirrored push. So the instructions have been included in the assignment 1 and the lab 3 documents. So if you downloaded them previous to last night and are working off that copy, please update your copy of assignment 1 and lab 3. They now include instructions on how to get those. Particularly, one could make the argument that for assignment 1, I could just post a zip file with the code in it. But the purpose of this course, this is Computer Science Practice and Experience Development Basics. So, learning how to manage these Git repositories in order to submit your assignments and your labs and eventually the exam, that is a learning objective of the course. I'm requiring you to use Git because that's also learning. You're learning how to use Git by using it practically to do practical things, like submit things. That's the whole point. The whole point of this course is to get you actually using the tools we're talking about. So, anyway. So, at any rate, this type of technical hiccup is, it happens when we're doing, such extensive degrees of surgery on the course materials as they currently exist. If you weren't aware of this so far in the course, we're basically we are generating a lot of new content this semester. Most of the labs are being generated, like 6 out of 10 of the labs. Well, actually, it turned out 7 out of 10 of the labs are being generated more or less from scratch. About half the lectures are generated from about 30% of the content already existing. The other half of the lectures are being borrowed from a second-year C course that I teach to the mechatronics students. So, or I did last year anyway. I don't know if they want to hire me for it again. But anyway, this type of technical thing happens, and the only thing that we can do is fix technical problems as quickly as we can once we know that the technical problem exists. So, we'll try to squeeze in the fixes to any more technical problems that arise before the deadline for whatever you were having technical issues on. But yeah, anyway, so that's information about Lab 1 and 3. I'm sure I have lots of questions. Let's just see. Hop, hop, hop. My camera broke again. How do I give you access permissions? Access permission... Oh. On GitHub, you mean. Email Mark about it. He's been the one handling. He probably knows this already because he's probably answered that question for 3 people already, so please email Mark about it. Hi! So, my camera broke. Let's see here. Yeah, it did, didn't it? Man, I look old in that picture. Jeez. It'll be nice. I'm hoping that I might be able to get a haircut this week. So that'll be nice for everyone. Won't have to look at my scruffy hair. Anyway. So, all that being true, let's get motoring. So we're on topic 5. We're going to talk about shell scripting. Let's see here. Yep, shell scripting, topic 5. Bing, bang, boom. And Let me just pop out the chat. It's fun to pop out the chat and have it running, so I can see when you guys have a question. I can just see it. I don't have to keep jumping back and forth. There we go. So there we go. Shell scripting. So let's talk stuff. So we've been talking about Bash. Bash is a shell. It turns out that one of the great strengths of Bash as a shell, and this is not unique to Bash, many other shells have this ability, but of course we're talking about Bash in this because it's the most commonly used shell for Linux type environments, so you know, it is what it is. But one of the most powerful things you can do with shell, with a command line interface like Bash, is you can set up scripts which automatically execute sequences of instructions with minimal human intervention. It's kind of like programming, but it's also kind of not like programming. It's like programming with programs. So it's a bit like meta-programming. So, we're going to talk about lots of stuff today, so we should get to it. As with all instruments, it is the man, not the tool, that makes the difference. The more subtle the tool, the greater the difference. Skill with a shovel makes less difference than skill with a violin. Shell scripting is a very refined tool. So, using your hands is lame. So far, we have barely dipped our toes into the vast ocean that is the Bash environment. It's time to level up our skills. So far, every command we've used has been entered into a Bash prompt, or we've selected it manually in some manner. Shell scripts allow you to collect shell commands together and execute them as one unit. So, we're going to have various examples today. Let me just find my root directory. Documents. McMaster teaching. 1XC3. There we go. Boom, boom, boom. Code. Make directory topic 5. There we go. Change to topic 5 directory. Clear screen. There we go. Yes. So, why use shell scripts? This is an advanced skill. We're only just getting into Bash. Why am I throwing shell scripting at you? Well, shell scripts are fast, versatile, and reliable. As a beginner, it might actually benefit you to write up some Bash scripts, because these sorts of routine tasks while you're learning, you know, you might make some mistakes in the repetition. But, you know, it's also good to do repetition in order to memorize things. So, you know, shell scripting is still very useful. So, the scripts are very, very fast, number one, because you're not waiting for a human to type anything, right? Most of the time that a computer takes to do anything is spent waiting for a user to type something in or to click on something, right? So because you have removed from the equation the requirement to wait for a user to say something, in most cases anyway, shell scripts can execute extremely quickly. They are also very versatile. Any command that you can put into a Bash prompt is something that you can use in a shell script, in a Bash script. So we have the full expressive power of your entire computer system, right? Because the Bash prompt allows you to run, you know, pretty much any any executable file that's in your file system in various ways, right? So, you know, yeah, so this is like automating the computer itself to some degree. And that's a good way to draw a mental distinction between this and programming in the regular sense, right? When you program in the regular sense, if you write a C program or a Python program or something, you're manipulating variables, right? When you're bash scripting, you're manipulating programs themselves. And of course, one of the great advantages of doing anything, like scripting up anything, be it a program or a bash script, is that because it's been written down, it will be repeated in the same manner each time. If you had to type everything out every time, you're more likely to make errors. The only catch, of course, is that shell scripts take time to set up and are somewhat harder to work with and debug than traditional programs. There's certainly an element of you want to get it right the first time when you're working with a bash script, because when you're working with you know, I've talked to you guys before about how programming, like working in Bash inside of a Linux environment, is a bit dangerous because Linux essentially trusts you to not be an idiot, right? If you do an idiotic thing, like delete your operating system, Linux is not going to help you out of the hole that you've dug for yourself because you deserved it. And because Bash scripting is a mechanism for automating all of these things that could make you have big problems if you use them incorrectly, you can, you know, to the degree that one command can mess up your whole computer system, a series of commands that execute without any human supervision whatsoever can seriously mess up your computer system if you're not doing them correctly. So you have to be careful. You have to be careful when you're doing bash scripting. There's also like a general feeling of like, you know, try to get it right the first time with a bash script. You know, and essentially, you know, the reason you try to get it right with the first time with a bash script is you don't have the compiler to complain at you when you've done things incorrectly. Go fix your mistakes, and then I'll compile your program for you. Because essentially every line in a bash script is just fed into the bash interpreter. It's not checked for accuracy or consistency or any of things that you would want to check a program for before being run. It's just run. So try to get it right the first time. Loose scripts sink ships. Here is how you create these very, very dangerous shell scripts. First, you create a file with a .sh extension. So, for example, example.sh. ls, there we go, example.sh. Let's give this thing some contents. We're going to do basically the hello world of bash scripting. Get it? Example. You can also use Emacs. Let's use Emacs, just cause. Ooh, so incidentally, I realized that a lot of you are going to be trying to do programming work in a non-GUI environment if you're logging in through the Pascal server. So I had Derek install Emacs on it for you. So you now have an alternative to Nano. Emacs is a really good thing to learn. We're not going to cover Emacs specifically in this course, but it's reasonably easy to learn Emacs. Essentially, the key to learning Emacs is understanding the command system. And the shortcut to sort of bug out the command system in Emacs is if you hold Alt and press X, you can type the names of commands manually, like save. you know, and then if you press tab, it'll show you all the different types of save things that you can do. But yeah, anyway, Emacs is the it's the editor that thinks it's an operating system. So shebang bin bash, that tells you what shell environment this script has been written for. Echo hello world. Save that up. In Emacs, Control X, Control S is save. Boop. Incidentally, you guys alive there? Give me a heartbeat. Tell me that you're still alive. I'd hate to be talking to no one. So we have a script, right? In theory, we should just be able to execute it. But permission is denied if we attempt to execute it. So there are a couple of ways of fixing this problem. The command line way is to use chmod to add executable permission to this file. So when you have files in the file system, the primary thing that distinguishes one... Yeah, Alex is alive. Awesome. Excellent. Wonderful. The primary thing that distinguishes a file that can be executed from a file that cannot be executed is the fact that that file has executable permissions enabled. Also, it needs to be something that can be executed, like it needs to be a binary file, or it needs to be a shell script or something like that. But essentially, a script like this has to have executable permission in order for you to actually be able to execute it. So, chmod add executable permissions to example.sh. There we go. Now, if we ls, you can see example.sh is now green. Green is, of course, the color used in this Ubuntu Bash environment to denote files which have executable permissions. Blue are folders, greens are executables. So it's kind of interesting because, like, most of the time, you guys, like, up to now, you guys have probably thought of executable files as being binary files that you can't open or see. You know, you can't open up a binary file and see what's going on in it because it doesn't make any sense to you. But because these shell scripts are encoded with, you know, regular character sets, you can actually, you know, go in and modify them and such. So you can modify it after you've made it executable. Example.sh. Hello world. It echoes hello world. Echo is the shell script equivalent of print. Yes, good. Awesome. Adam's heart is broken. So there you go. That's how you execute a shell script. Hope everybody's following along. So, the first line of my script is called the shebang. The shebang is indicated by octothorpe exclamation mark. This line indicates which program we wish to use to interpret the script. For example, you can run Python files as scripts using user/bin/python. And I'm sure if we go to user/bin and take a look in there, we'll probably find Python in here. Doop-a-doop-a-doop. User bin, everybody should know what user bin is after having done the lab last week. My goodness, there's a lot of stuff in here. PyDoc, PyClean, PyCompile, Python! There we go. Python, there we go. So, the way that it works in Linux is that one will link to the correct version, the correct most recent version of Python. You saw like Python 3.6 in there, and Python 2.7. The reason it has to have that is like for the sake of compatibility, some older programs will have been written for Python 2.7 and may or may not compile in Python 3.6. Like once you get into computers and stuff, you'll realize that it's often a very perilous thing to update a program to the next version because you might break a bunch of dependencies. Anyway, alternatively, we can pass the script into the interpreter we want directly. So, rather than performing the // we can say bash example.sh, and it also works. This is also how you run Python files. So, Python is an interpreted language. It runs inside of the Python interpreter, and in many ways is very similar. Like, the way that Python works is very similar to the way that Bash works, because Python also feeds a Python script in one line at a time and brings you the errors as it encounters them. As opposed to a compiled language, which will give you all your syntax errors up front, because it parses everything first. So, to some degree, the manner in which you're familiar with Python working is how a Bash script works to some extent. So, let's introduce variables. Let's get complicated. So, you assign a variable with the equal sign, but do not leave any spaces. This is very important for Bash scripting. So Bash scripting, it's different in a lot of ways to how something like your Python or your C will work. Let me just bring Emacs up again. So, in Bash scripting, when you have spaces, the space gets included in the value of the variable. So, notice that there are no quotes here. Because there are no quotes, the string itself begins immediately upon termination of the equal sign character. So, var1 is equal to hello. var2 is equal to goodbye. If you echo var1 and echo var2, let's save that up. And close that, duplicate, there we go. Run example.sh. We've got hello and var2. So this is another difference between a Bash script and a traditional programming language. In a traditional programming language, just using the name of the variable automatically substitutes the value of the variable. In Bash scripting, you have to prepend with the $sign character. The $sign character says, I am substituting the value of this variable here. Otherwise, it'll just use the variable name itself. I know this is a little bit, this is kind of bizarre, right? But don't worry too much about it being bizarre. It's actually fairly, it's more similar to the concept of macro substitution in C, which I know we haven't covered yet, but, hear me out. Don't think of these as variables in the sort of C or Python sense. Think of these as substitutions. So when I call or when I use $sign and then a variable name, that is a command for character substitution. So whatever the value of the variable is, that gets substituted in where that is, right? That's how this stuff works. So, yeah. Hopefully you guys are following so far. Yes. Here we begin the essential weirdness of bash scripting. Notice how we're working with strings here, but there are no quotes in sight. Notice also that a variable is not substituted into a command unless preceded by the $sign. Keep in mind, everything in here also applies outside of the script file. So, another cool thing about bash is that you can, like I said, everything that you can do in a bash at a bash prompt can be put in a bash script, and conversely, anything that you put in a bash script can be done from a bash prompt. So, var1 is equal to, multiple concussion. Echo var1. Multiple concussion. If you just ask for var1, it says command not found. If you perform the substitution, multiple concussion, command not found, because this is a bash command, right? In bash commands, whatever program you're executing, that's always the first thing. The first argument is separated by a space character. So, like if I were, for example, to say var1 is equal to ls, for example, and var2 is equal to the LA flags, then if I do var1, with the substitutions, of course, var1, var2, then it performs ls with the LA flags, right? It substitutes the characters and then executes. Are you guys getting this so far? I know this is like a very different way of thinking. Give me a thumbs up if you're following. So, don't quote me on that. In bash scripting, quotes do not denote string values. Bash separates arguments by whitespace. So, this is similar to how Haskell separates function arguments with a space character. Quotes allow us to include whitespace in arguments. You may have noticed, sometimes I have a tendency to try to reduce the number of space characters in, like, my files and folders inside of my system. That's because if you, for example, if I go back up to 1XC3, you'll notice there are quotes here, right? If I go, so if I try CDing to 1XC3-summer 2021, too many arguments, because it considers 1XC3-summer and 2021 to all be arguments. So, if I enclose those in quotes, then these spaces are included in the argument, and the quotes themselves are not considered to be part of the input. Thumbs ups! Excellent. So that's how you deal with spaces. And, of course, because that is true in the bash command line environment, that's also true in bash scripting. Code. Topic 5. Good. So, there's also a difference between single and double quotes. Single quotes preserve input verbatim, and double quotes preserve the input but permit substitution. So, if I were to say something like, var1 is equal to hello, right? Echo var1 world, I get hello world. If I use single quotes, I get verbatim what is inside of the string. So no substitutions are performed. So that could be useful, possibly, in some instances. So, you know, so why is it like this? Why is it like this? You would, like, everything has to do with characters here. All you're doing is you're trying to perform character manipulations to get the commands you want, and to, like, maybe generalize the commands you want. I have a question. Could you make a bash script to open up your local Git repo every time? Well, I don't know. So I don't know if the idea of opening up a local Git repo, like, are you talking about cloning one? Cloning is not something that I would necessarily put into a bash script because it's like a one-time operation. But yeah, you could, like, if you wanted to automate a certain process that you're probably going to be performing quite a lot, you could totally do something like git add dot git commit message script commit git push. And that would, like, then you could perform all of these actions in one operation, right? You'd lose some diversity with respect to what you wanted your commit message to be, but not necessarily. So let's actually go with this. Let's use this as a working example. So, the following special variables are reserved for managing arguments in bash scripts. So, $1 through 9, these are the first 9 supplied arguments. $@ is all supplied arguments, and $number is the number of supplied arguments. So, if, for example, we wanted to include the message as an argument to our thing that automatically performs these Git operations, we would just do $1 and save that up. So this is not going to work because it's not inside of a Git repo, but, you know, we can, well, I suppose we could create one, couldn't we? There we go. So now that's a Git repo. ls all, you can see .git is in there now. So if we call example.sh with argument, this is my first commit. Yeah, so you can't push, of course, because it's not a remote repository, but the other commands will have been performed just fine. So if we git log this, oh, does not have any commits in it yet. Here we go. All right. Maybe if I put it in quotes. There we go. There we go. So you have to put it in quotes, which makes sense. I mistakenly thought these quotes would be preserved, but of course they weren't. So this is my first commit, you can see there, and then, you know, if I wanted to add another commit message, you know, whatever. You can add it as an argument to the shell script, in the same way that you add arguments to Git or anything else. And then git log, you can see, there we go, we have a commit. So yeah, hopefully that answers your question. Get into the file location on your bash and start doing stuff. Oh yeah, like if you wanted to make a shortcut, like if you wanted to make a script like goto.sh, and you could make a bunch of, like, you know, go to labs, and then that would, you wouldn't have to enter CD all the time. Yeah, absolutely. Why wouldn't you? Of course, you know, why wouldn't you? Because it takes time to script out the bash script, that's why. So, anyway. So this is introducing the idea of ifs as well. We have we're going to talk about ifs a little later on. So I realize I need to move because I'm kind of lagging behind on this particular slide set. So you can provide arguments to a bash script in the same way that you provide arguments to any other bash command. Yes, as I demonstrated. Script it and they will come. So here are some additional special variables that you have available to you in bash. $0 is the name of the bash script. So echo, there we go. That echoes the name. The process ID of the current script is $. That's cool, so you can have a script that kills itself by killing its own process ID. User, hostname, random, home, and path. User is the username of the user executing the script. So user. Oh, save that. So that's Nick. You can see Nick. Host name. So these are special variables that you have that are already set up by default. So the host is my computer's name that I gave it upon initialization, which I thought would be clever to specify the operating system, which, you know, man, the mistakes you make when you're configuring systems, eh? Random is a random number. Home is the home path of the user executing the script. So that would be home/Nick. And path is path is an interesting one because it tells you all of the different places where binary files can be found that should be executable from the bash prompt. So if you've wondered how Linux knows where your executables are, it's because there's an environment variable that specifies, you know, user/bin, user local bin, all of these folders where the binary files are kept. These are kept track of inside of path, the path variable. In fact, when you're installing something to a local folder, you have to modify the path variable in order to get that, in order to be able to actually access it from the bash prompt. Otherwise, you have to address it, otherwise you need the full address, right? And you need to, like, call the binary with its absolute address path each time, which is a terrible idea. So these are called environment variables. A common part of manual installation in Linux requires setting environment variables for the program you're installing. To do that, we need access to Bash's startup routines. So, let me just see that we have any questions. Yeah, okay, good. When Bash starts up, it begins by looking for the script /etc/profile and executing it if it exists. So there are a couple of startup routines for Bash. So every time you open up a Bash shell, like for me, each one of these tabs is a separate Bash shell, right? Each time I've opened one of these up, it's executed everything that's in etc/profile. Changes here affect all users, but require super user privileges to modify. So if you make changes to profile, that affects everybody. And, you know, that makes sense because that's stored inside of the sort of operating system folders that are accessible from root. They're not accessible inside of your own home directory. Next, Bash looks for home/bash profile, bash login, or profile in that order, and executes the first one it finds that works. So, if you go to your home directory, cd tilde, that's your home directory, and if you ls all, you can, like, this is an actual user that I use, so you can see there's a lot of stuff in here. If you can see that there is a file in here called .profile. So this .profile file, this is executed as well every time a bash script is, every time a bash shell is opened. However, it's only opened for my user, right? So if I had multiple users on this device, like Nick, Tom, and Harry, Nick's profile file only executes when Nick opens a bash session, and the same thing for Tom and Harry. Changes here do not affect other users, and super user privileges are not required to modify them. So if you're looking on the Pascal server for where you might be able to modify path or something like that, it's going to be one of these three files. I'm not sure which one Pascal uses specifically, but it's one of these three. If bash is invoked in a non-login shell, i.e. a bash session not bound to a terminal, it will use bash rc, home/bash.bashrc if the file exists. So non-login shells are things like, like window interfaces and stuff like that. So yeah. Good. Saving the environment. In order to set environment variables, all we need to do is add them to one of our bash's startup scripts. We already know how to assign a variable. All you have to do is open up the .profile file. So like, emacs.profile. Take a look in here, and you can see I've already modified my path a couple of times. So this line here allows me to add more paths for my computer to look for binary files on, and it includes all things that were already assigned to path, because you can see this is kind of like the bash equivalent of a plus equals operation, because we're recursively including the variable as it already existed. Well, maybe not recursively, but anyway, hopefully you get the idea. So yeah, any modifications you make inside of here will exist for all bash sessions that I open up. So, so there you go. Variables assigned in this way are scoped to the bash shell that created them, but are not transferred. So, in order to transfer environment variables to other subshells, and interestingly, when you execute a bash script, that's considered a subshell within the shell. You have to also call the command export, and you just include it on the same line as you're assigning the variable. Using the export command makes the variable accessible and available to the creating bash session as well as all sub-processes. So in general, that's the one you want. Now, if you're modifying an existing environment variable like path, you don't necessarily have to, because, path is path, and everybody needs path. But if you're making your own, then, that's how it works. Incidentally, if you type env, you can see all of the environment variables currently existing inside of your bash prompt. I know I'm throwing a lot of information at you, but that's kind of the way this works. So, recall that bash uses path to look for executable programs. If you are adding a new program and you don't want to have to navigate to the folder in order to run it, add it to path. export path is equal to path colon path to some directory. Add the above to .bash profile or similar, and then essentially whatever binary files are located at the file path that you've added to path, those will be callable, just like ls, just like cd, just like anything. Calling echo will show the different paths that path looks through as a colon separated list. The above construction is similar to Python's plus equals assignment operator. Any executable binaries that at the specified directory can be used as commands. The only catch is that you have to restart your bash session so that the changes take effect. That's right, because this script is executed when the bash shell opens up. If you haven't opened up a new one, then this change won't have taken effect. So when you've modified .profile, the thing to do is to log out of Pascal if you're doing it on Pascal, or close down in some way the bash prompt that you're in, and then open up a fresh one, and the changes will be made effect. So you don't have to restart the whole computer, just the shell. So there you go. You might have to log out and back in again, though. So anyway, meanwhile, at Linus Torvalds' house, quote, "To be a nemesis, you have to be actively trying to destroy something, don't you? Really, I'm not out to destroy Microsoft. That will just be a completely unintentional side effect." And if you notice what's off about this picture of Linus Torvalds' house, then you will get the joke. So, beware of white space. White space, that is to say tabs, spaces, and new lines, have more semantic content in Bash than in any other language except perhaps Haskell. I think a number of you will have taken Haskell. Or I don't know. I think 1JC3 is running concurrent with this, actually, so you had maybe a choice between taking my class and I think, is it Curtis? I think Curtis is teaching it this summer. Possibly. I don't know. Anybody in 1JC3? Anyway, give me a thumbs up if you're still alive and paying attention. So anyway, so think for a moment about the way that you structure commands inside of the bash prompt. Spaces are important because they separate arguments and commands, right? Space is an argument application operator. And I know it's strange to think about a space as having an operation attached to it, but that's how it works. Space in Bash is argument application in the same way that space in Haskell is function argument application. Bash takes every character literally. This is why Bash is difficult to work with. There's when you're writing a Bash script, there's far less flexibility in syntax than C or Python. I would actually argue that Python is a lot less flexible in its syntax than C is, but this is why I say it's important when you're scripting in Bash to try to get it right the first time. So because the types of errors that you're going to find are going to be ludicrous and strange. So, for example, var2 is equal to hello. This is good. No spaces. Very nice. var2 is equal to hello. This one, var1 space is equal to space hello. This is evil. Evil! So, let's try it out. var2 is equal to hello. Echo var2. Hello. There we go. var1 is equal to hello with spaces. var1 command not found. It thinks that you're assigning, that it thinks that var1 is a program with arguments equals and hello. So if we tighten up the 1, it still thinks that. Command hello not found. So, you know, so it's gonna mess things up. It's gonna think that you're doing things that you're not if you include the spaces. So just don't include the spaces, okay, guys? Cool. All right. Bash has no types. This is another thing. Any programmer not utterly ruined by Python knows that variables have types. Actually, it would be difficult to program in Python if you didn't have any concept of types. So, in C, we have integers, characters, arrays, or strings, and characters, right? 1, hello world, and exclamation point. In Bash, however, this is some text, this is some text, this is some text. It is more correct to think of variables in Bash as being more like macros in C than variables. They perform direct character substitution regardless of syntactic construction. This is, so one way to think of it is everything is a string, right? But it's really more like what you're doing is you're programming with pieces of characters that can pose together to form commands. Because of this, concatenating does not require an operator. So in Python, the way that you concatenate things is hello plus world. So the plus, the addition sign has been mapped to string concatenation when applied to objects of type string. In Bash, you just perform adjacent character substitutions. So I may have already shown you this, but var1 is equal to hello, var2 is equal to world, not world. So echo var1, hello, echo var2. Oh, and the other thing about Bash is everything is case sensitive. Everything is case sensitive. World, and if we wanted to do hello world, var1, var2, hello world. If we leave a space, because we want a space in there, it puts a space in there. But, you know, that's only because of the way that echo works. If you tried doing that with a, like, ls command, it's going to consider those to be different arguments. There you go. Substitution. If you want to assign a... Pardon me. Let me take a moment. Yeah, actually, you know what? Well, I just prompted you guys for questions not that long ago. So, let's talk substitution. If you want to assign a variable to the output of a command, you need to use command substitution. So, command substitution is $, then brackets, and then you include a command inside of the brackets. This allows you to redirect the results of standard output to intermediate variables and then back into standard input. You can also do this with pipes, which we will be covering later in the course. Later on in the course, we're going to talk about pipes and filters. This is a little bit of pipes and filters stuff, but you know, man wc, what does it do? Print new line, word, and byte counts for each file. So, cool. Oh, yeah, I need to get back into documents, McMaster1XC3. Yup. Topic 5. Yep. There we go. So, wc example.sh. So there you go. wc-l. So that gives 4. So that's because the script has 4 lines, even though 3 of them are blank. If I subtracted some stuff from here, it would get out 1, so it's got 1 line in it. So if I store that to an intermediate variable, I have to do $ braces wc-l example.sh. Now, if we echo var, you get the results, right? So you can redirect the outputs of commands into the inputs of other commands. grep, incidentally, that allows you to search the contents of files. So grep -ra shebang. You can see it exists inside of example, but shebang also exists inside of all of these all of these scripts that exist inside of the Git repo that I set up in this directory. And you can see some of these are using sh as a shell. One of these is using Perl, which is interesting. You don't see much Perl. Kind of an uncommon. It used to be a lot more popular, but it's sort of decreasing in popularity. Perl would have been popular around the time that Git was being invented, which is to say, the 90s. Languages of the 90s. Subshells. Code executed inside of a script is considered to be a subshell of the shell you execute it from. Subshell. Get it? That's a visual pun. Ha! Dad joke. Variables within a shell are not automatically available within the subshell processes spawned by the shell. So, again, this is kind of hammering in the idea that you have to export variables if you want them to show up in subshells. Think of it like a global variable in Python. To use them within a function, you have to declare them. So, essentially, if I had something in here, like I wanted to echo my var, right, inside of this script, example.sh, and if I assigned my var as having a value of what did you do with my peanuts, stop. There we go. Echo my var. What did you do with my peanuts? Oh, it doesn't like the exclamation point. Anyway, so this variable exists within the shell that is corresponds to this terminal window. If I try executing example.sh, you will find that the variable is blank within that shell. So it doesn't exist. In order for it to exist, home, I have to export. There we go. And now it does exist. So this is kind of like the idea of global variables in Python. In Python, if you want to use a global variable within a function, you have to declare it as being global within the function. In bash scripting, in order for a variable to be global in that sense. You have to declare it as a global variable by performing the export command. Boop. Expressions of dissatisfaction. You may be asking yourself, okay, but math? So integer arithmetic has to be performed inside of the double parenthesis environment. And this is really just syntactic sugar for the expression command. So it turns out you thought you had to load the Python interpreter to do basic math inside of a command line environment. Turns out there's a command for that, expression. 2 plus 6 minus 8, 9, divide by 2. The answer is 4. Somehow. Order of operations? Huh? Weird. Anyway, so if you wanted to, 4.5, 8 minus, oh, because it's integer arithmetic, right? So it would drop the decimal. Yeah, okay. Life makes sense again. I don't have to stop. I don't have to quit my day job and go become a Central Park vagrant because math has stopped working. So, if you want to perform that math inside of a bash script environment, you can either do expression like that, or you can perform it, inside here. Now, the thing about that is, let's see if this works. Yeah, it does. So, with the expression, so one of the things that you get as a consequence of that is, as a consequence of using the double parenthesis environment, is that you don't have to space things correctly as if they were arguments to a command. You can just math. So there are advantages to it, but essentially that's what it does, is it takes it, parses it, hooks it up to expression. A full listing of available expressions is in the expression manual page. Use the source, Luke. Man. Expression. Ta-da! So there you go. All kinds of stuff. Alright, so before we get into conditionals and loops, I'm going to ask you, do you have any questions so far? Lab 4, which is occurring tomorrow, is going to require you to do some reasonably simple scripting operations. Mostly having to do with creating files and directories, deleting files and directories, making backups of files and directories, that sort of thing. Give me a thumbs up. So yeah, like, one of the things that's absolutely excellent about Bash scripting is, like, it really allows you to invent your own workflow, you know? Like, any commonly performed task can be automated with a Bash script. Absolutely. And now that you... Pardon me. Now that you know a little bit about variables, you can make these scripts more dynamic, you know? You can automate your tasks much more efficiently. And this, like, learning how to Bash script is the reason we are using a command line environment for this course. Like, if you get a job programming, doing programming for a living, these are the types of efficiencies that you are expected to come up with as a programmer to make your workflow more efficient. There really is an ethic in programming of, like, work smarter, not harder, you know? And then work harder. Work smarter so that you can work harder. The more that you can get done, the more valuable you are to your employer, and more valuable to yourself, and the more money you make, and money is good. So, you know, like, this is really where, like, Linux really pulls away from the other two major operating systems in terms of the utility of it to a programmer, right? If you can write a bash script that shaves, you know, if you can write a bash script that shaves, like, 30 seconds off of an operation, and you perform that operation, you know, 4 times a day, right? By the end of a week, you've saved like 14 minutes, about 15 minutes, which means you've saved yourself an hour of work every month, and you know, 52, like 12 hours of work over the course of a year. So you've saved yourself a day and a half of productive work by writing a bash script that saves you 30 seconds 4 times a day. Like, this is the type of math think that you have to that you need to engage in to really understand the value of bash script. Because there's really no point in using your hands if you can get the machine to do it for you, right? Work smarter, not harder. And then work harder because you're working smarter. So anyway, if statements. So, conditionals. We have the ability to perform conditional operations inside of a bash script the same way that we perform conditional operations inside of a regular programming program. So, they're a little bit different in syntax. The primary differences are rather than using indentation or curly braces, you're using an opening if and a closing fi, which is, you know, kind of strange. But that actually, I believe that that derives from Fortran syntax. That's right, formula translator. You include some test inside of square braces. You then put a semicolon and a then keyword, and then you include your commands. If the test comes out true, the commands are executed. Otherwise, not so much. If you want to add an else case, then you just, you know, add it in the manner that you might expect, given the syntax. If you want to perform the logical conjunction of 2 tests, i.e. take the and of them, double ampersands, just like in C. If you want the logical disjunction, that is, the or of 2 tests, you use double bar, again, same as C. And if you want else, if you want something else, then we've got elif, just like in Python. So again, the syntax is a little weird, just like everything else in bash script, but here it is. So we've also got, so this is, the square braces are a reference to the test command. So again, just like expression, we can call test outside of an if environment. So test. Test, check file types, and compare values. So you've got all kinds of different tests that can exist. Right? For example, n checks to see that the length of the string is non-zero. GT is greater than, LE is less than. So let's bring up our script here. echo comparing two arguments. If first argument is greater than second argument, colon, a semicolon, then echo one is greater than two. Phi. Save. Quit that. Execute example.sh. 3 and 9. There we go. Oh. Let's see. Gotta leave my spaces. Haha. Else echo 1 is not greater than 2. There we go. Comparing two arguments. 3 is not greater than 9. 10, however, is. So that's how you perform tests. Yes. A full listing of the sorts of tests you can perform is in the man page, of course. And the test command can also be used as follows, just like we could use the expression command explicitly inside of it. We didn't have to use the braces. We can also do the same thing with test. So if your keyboard doesn't have square braces for some reason, you can just substitute the test command, and it works the same bloody way. Here is a non-exhaustive list of comparisons available in test. So, bang expression, that's an expression. X is true. Is that true? It might be X is false. I might have made a mistake on this test. Yeah, that's false. I don't know what I'm talking about. I'm going to modify these, update these slides. N, length of x is not equal to 0. X equals y, x and y are equal. Not equals, x and y are not equal. These are operations over strings. Dash EQ is for integer equality. Dash greater than, dash less than. Dash E, item exists. An item is either a file or a directory. Dash F, X exists and is a regular file. Dash D, X exists and is a directory. Dash X, file X exists and is executable. So, for example, if we take a look in here, test-x example, yes. And if I modify the name. So it doesn't display anything, but we weren't asking it to. So it really doesn't display anything unless you like hook up the output of it to a variable or something. So var is equal to that. Let's take a look inside. Echo var. It's nothing. It's probably setting flags. Internal flag stuff. Anyway. So, any questions about that before we talk about loops? Give me a thumbs up if everything's cool. My thing is still working, surprisingly. Good. All right. So let's talk about iterating. So within the Bash environment, we have 3 different types of loops that we can use. So we've got for in loops, which are probably something you haven't seen before. Although oh wait, no, because that's how Python works. Scratch that. So the for in loop is somewhat similar to the Python for loop, except for Python, you're inning over a data structure, whereas with Bash script, you're performing the for in over a collection of characters space separated. You have a C-style for loop. This is your syntax. And you have a while for loop, or a while for loop. You have a while loop. Notice our loops are terminated by done statements. They all have a do. So let's try these guys out, eh? For item in, so input is equal to 1, 2, 3. For item in input, do echo item, done. For I equals 0, I is less than 10, I plus plus, semicolon do, echo, counter, and then the value of I. So you can, like, while Bash script is primarily useful for, invoking commands, it is also something that you can do general programming in if you want to. It's kind of a pain in the butt, so I wouldn't recommend it. But, it is what it is. And then you've got your just plain old while loop. Your old friend while loop. Uses the regular test function, the same test function that the if statement used. So, if count is less than 10, do echo count. Count is equal to evaluate count plus 1. Done. Save that up, and let's execute that script. Now you can see. Syntax error. Did I include too many $signs? Looks like I may have included too many $signs. Line 21. I did. There we go. So there you go. That's how these things work. You should all be pretty good at loops by now. So by default, Bash separates inputs and arguments by whitespace. However, you can actually set that. So ifs, if you set ifs, IFS, to something other than whitespace, then you can get things to be separated by things other than whitespace. If you'll notice, that's how... pardon me. Oh, terrible. Sorry. If you notice, that's how the different directories in path are separated, is using colons. So you can set that. It's also, this is also how you unset a variable. So if I think I've got like something like var in here, or var1. Yeah, there we go. If I unset var1, then it no longer has its data. My camera froze. Of course my camera froze. I was just bragging about how my camera hadn't frozen yet. And that, obviously, the gods of technology hate me. Yes. So there we go. That's shell scripts in a nutshell, so to speak. Last slide comic. Rob, you use Linux? Come quick. To disarm the bomb, simply enter a valid tar command on your first try. No Googling. You have 10 seconds. Rob, I'm so sorry. Tar is used to compress archives. It's the equivalent in Linux of, like, WinZip, I suppose, except WinZip is terrible. Whatever miscellaneous zip program you use in Windows, when you haven't quite realized yet that Windows integrated that right into your right-click menu quite some time ago. You don't actually need an external zipping program anymore. Send to compressed archive. That's how you zip things in Windows. Anyway, you use the tar command in Unix, so, and its arguments are like ridiculous, and nobody can remember them. It's like, you know, tar CVF, tar like XAC, etc., etc. Anyway, that's just a joke. So, are there any further questions about shell scripting? If not, give me a thumbs up. You guys feel you have a decent handle on it? How bad does it seem? Talk to me, guys. Could I go over conditionals again? I absolutely could go over conditionals again. Okay, seems okay, but like the awkward child of everything. Yeah. It's kind of like, it's almost actually the inversion of that. It's not necessarily the awkward child of everything, but like it's like the awkward grandfather of everything. Like bash, like shell scripting predates a lot of this stuff. Actually, that'd be interesting. I wonder how old is bash? Is bash scripting? Oh, okay, so that's actually not that bad. Okay. Shell scripting in general. How old is shell scripting? Yeah, maybe it is the awkward child of everything. Strange. Anyway, I would have assumed that the bash prompt itself would have been would have been invented around the same time as like Unix itself, but perhaps I'm wrong. Anyway, it's happened before. Conditionals. So, to go over it once again, if statements are closed by fi, you gotta follow this syntax. You gotta put the spaces where the spaces go, because this is bash scripting and the spaces matter. The tests are references to the test command. If you want to see the full listing of all of the different types of tests that are possible using the test command, then you can pull up the man page. A and O, those are logical commands. There are lots of string commands, so strings are either equal or not equal or of length 0. There are lots of integer commands, integer comparisons, and there are a bunch of file operations. So, if I were to go up a directory, if I were to say test is directory topic 5, I would get a yes. But again, you can't. Unfortunately, with these ones, it's impossible to see the results in the bash prompt because it's setting flags which are being read by the if construct. But yeah. So essentially, manner of use. Write up a test. Take the arguments to a test, drop it inside of these square braces, and then it functions pretty much like any other if statement that you would use in any normal programming language. A lot of these operations, it's like you're trying to test to see if like a directory exists or if it has X, Y, or Z files in it, because a lot of bash scripting, at least at a sort of entry-level bash scripting, is like file manipulation commands, right? Automatically taking backups, for example, is a really useful thing to have, and a really easy type of bash script that you can write for yourself. But hopefully that answers your question. Hopefully that's good. Any further questions? So I guess I should talk a little bit about your lab today. So lab 3, I was working on lab 3 last week. Essentially, what I've done is I've created the worst Git repo in the history of the world. That's probably not true, but essentially the idea is to give you guys experience with merging and resolving conflicts in Git repos. So I've set up a repo that has 11 branches in it, where each one of those, well, maybe not each one, but essentially pieces of good code have been hidden like Easter eggs inside of each of these 11 branches of code. And as you merge the branches together, the idea is for you to resolve the conflicts in such a manner that you keep the Easter eggs, and then at the end you have a program which does command line chess. At least a very rough first approximation of command line chess. The author would prefer to call it a program that exhibits chess-like behavior rather than an actual chess program, because it doesn't have a second player and all of the pieces are white pieces, because I didn't have the time or energy to program the black pieces and it was already big enough to be a good lab. So yeah. So it's gonna, that's the exercise for Lab 3. I performed the merge operations myself to construct the, the program from all of the branches. Took me about 20 minutes. So I'm hoping that if you guys have an allocated amount of time for that lab of 4 hours, 2 in class and 2 outside of class, because of the registrar's goof up, hopefully 12 times the amount of time it took me to complete the task will be enough for you guys to complete the task. So, yeah. Anyway, if there's nothing further, I think I'm going to log off here and leave you guys to go nuke your pizza pockets in advance of the lab. Uh-oh. Okay. Yeah, anyway, take her easy, folks. Take care, and script on.